Hello. So what I want to focus on for the next sort of hour and 3/4 for today, and then for 2 hours for a similar session next week, but next Wednesday. Remember, so today's Thursday. Our one next week is next Wednesday. Is this sort of idea of getting a good start in year 12. So you kind of know the cliche, start as you mean to go on. I think it starts as they need to go on. So what do you do in September, October, November? What do you do in the first term of year 12, which starts to develop those algebraic skills they will need for A-level success? So that's my purpose. That's what I want to sort of focus on. And today we're going to focus very much on what you might call sort of abstract algebraic skills. And then next week we'll connect those with graphs, and we're looking at algebraic and graphical skills. If you're on the Twitter, if you engage in social media and you want to say anything about what we're doing this afternoon, hopefully you'll say you're enjoying it. I hope so. If you could include us at King's Maths School with only one S. It should be Maths School, but it's not. It's kind of Maths School or something. And they're the hashtags I often use: teachers always learning and learning together. So if you're on the social media and want to sort of share that with people, then please do so. So these are my objectives. This is kind of what's been in my mind for the last week or so whilst I've been putting this together. I want to share with you topics, kind of specific areas. Within those areas, I want to share with you some examples, but also I want to make sure there's a rationale. So I can tell you why I've chosen these topics, why I've chosen these examples, so that you can, going forwards from here, think about developing a sort of core skills in algebra program. Now, for some of you A-level mathematicians, that will be consolidation, because they will be high retainers. They perhaps are coming to you with sort of 7s, 8s, 9s at GCSE. For some of your A-level mathematicians, this will be development, because they won't have very secure algebra skills. They might have 6s. They might even have 7s and possibly even 8s from GCSE and not have secure algebra skills. And of course, particularly at the moment, because they haven't been through necessarily the same sort of kind of year 11 summer term boot camp as they would have had were they doing GCSE. It's been much more varied across the schools, because of course schools have done their tags in different ways. So you are less certain what a student coming through the grade 7, student coming through the grade 8 means at the moment than perhaps you have been hitherto. So I hope there will be, so that's the idea. I hope there'll be things here which you can take and either turn into a program to boost the algebra skills of your year 12s when you meet in September, or to secure and build on the skills they already have. And all the time it's thinking for the long term. It's thinking long ahead. It's trying to avoid trouble ahead. What do I mean by that? Well, I think here are 3 questions. They're not literally A-level questions, but they could easily be A-level questions. So coordinates of the turning points, general solution of that differential equation, and then a mechanics question. Now, we're not going to solve these questions in detail today, because that's not the focus. But all of these questions, to be successful in answering them, all of these questions require algebraic fluency. They all, in the middle of the question, they all throw up some hideous algebra. And my experience of teaching students who are unsuccessful at A-level, who find A-level really difficult, is that what they haven't got that at their fingertips. I can't snap my fingers. I've never been able to. So imagine I'm going snap, snap, snap. They haven't got what they need. So it's not in the bag. They can't reach for it. It's not there. They haven't got the procedural fluency that they suddenly need a bit out of the blue. And it's not the beginning of the question. So question 1, quotient rule, or possibly a product rule. Lots of students can differentiate and get kind of 3 marks. And they know what they're trying to do to find the turning points. They know they need to set that equal to 0 and solve the resulting equation, but it's just the algebra. It's just too much. They haven't got the muscle memory. They haven't had the maths practice at solving that sort of algebra. So that's kind of what comes up in year 13. What can we do in year 12 to prevent that? Or at least try to reduce that. So question 2, so the first part often goes okay, so they separate the variables, they get dy over y equals d over x, they integrate, they get ln y equals ln x, assuming they remember the plus c, so they get, say, ln y equals ln x. So they write down ln y equals ln x plus c. And then, of course, it's incredibly tempting to write y equals x plus c. And then you go, well, no, that's not quite right. And they go, oh, yeah, no, of course, yeah, sorry, of course. It should be e to the power c, shouldn't it? And that's very tempting. Obviously, it's wrong, but we can't deal with it now in the middle of year 13. So what should we have done in year 12 to try to reduce the likelihood of that happening? At the risk of stating the obvious, these slides will be available to you afterwards. So, and with my annotations on, if you want to kind of sort of take screenshots, you're very welcome to, but the slides will all be sent to you as they are, and then you'll be able to use them for your own study and for training of your other colleagues. And then question 3. So if we're going to draw the picture, it will be sort of something like that. Kind of, I don't know, there's one string, there's another string. And there's my 5G, and there's my 20 newtons. And so yeah, they can draw the picture. They often reasonably okay at working out what the equations are. But then, as you can see it coming, there are 2 equations and 2 unknowns. There's some simultaneous equations, and then that's where they get stuck. They haven't got that algebraic muscle memory, that algebraic procedural fluency to solve the equations with confidence. And this particularly happens in mechanics, because suddenly you're solving quadratics, suddenly you're solving some simultaneous equations, suddenly you're solving a mix of linear and non-linear simultaneous equations. So this is what I'm thinking of. I'm sort of thinking of the sorts of things that cause problems in year 13, and then backtrack to year 12. What can we do about it? First of all, an apology, which is for today. I am Mr. Rush. So at 4 o'clock, I have to go at 4 o'clock because I've got another different session at 4 o'clock. So I may finish ever so slightly early if that's okay, about 3:58, and then I can't hang around for questions. But I'll make sure you've got my email. If you've got any burning questions you need to ask me, please feel free to email me. But also next time, Wednesday, I'm completely clear afterwards next time. So next time I can definitely stay around and answer any questions if you want to. So apologies in advance that I'm going to disappear slightly rudely at the end. In terms of the structure of this, then I'm going to do a bit of talking. I'm going to show some questions. I'm going to ask you to think about some questions. I will give you some time to do the questions, but I'm not expecting you to do them all in full detail. I'm certainly not going to sort of sit here in sort of silence for 10 minutes while you're doing lots of questions. I don't think that's the most efficient use of your time. You will have the questions afterwards to explore by yourself. When you are doing the questions, when I put the questions in front of you, please keep thinking about the structure of the questions. Why have I written the questions in the way that I've written them? Why have I designed the tasks in the way that I've designed them? What am I trying to draw out from the students, but through these questions? And that's something we can perhaps talk about in more detail next week, either in the session or after the session. So in all my teaching, I'm talking to you about sixth form teaching, but actually I teach across the entire age range. I teach in primary as well as in sixth form. I have on the same day once taught year 1 number bonds to 10 and Demoivre's theorem for year 13. I was working all through academy and I taught both on the same day. That was quite a bizarre experience. I have to say the year 1 were far more attentive than the year 13s were. But in all my teaching, I come back to the national curriculum. And the national curriculum says that all students must reason mathematically. They must all become fluent through, the underlining is my emphasis, varied and frequent practice with increasingly complex problems. So straight away, I'm just asking myself, is the practice I'm giving my students, is it sufficiently varied? Is it sufficiently frequent? And are the problems increasingly complex? And sometimes at the end of the week, I go, no, I haven't done that. It hasn't been sufficiently varied. There hasn't been increasing complexity. And in terms of solving problems, they must solve routine and non-routine problems. They can't just do the same old thing again and again and again. In particular, because they need to develop the skill and the habit, the attitude of persevering in seeking solutions. So this is taken verbatim from the national curriculum. When I'm training beginner teachers, and one of the privileges of my role is I do get to work with quite a lot of beginner teachers of NQTs or RQTs. I say, look, that's your job description. Basically, that's what should be, sort of stuck on the inside of your teacher planner. That's your job description, and you just have to be brutal with yourself. Have you done this? Have you lived up to these standards? So, in terms of today, then, I thought I'd focus on routine and non-routine these topics. So factorizing simultaneous indices and logarithms, algebraic fractions, and sort of what I call algebratization. So turning maths problems into algebra. Now you might go, hang on, what about inequalities? What about completing the square? I completely agree. They are fundamental algebraic skills. I think they're more appropriate for next week when we're looking at graphs. It would seem very odd to talk about completing the square and not talk about graphs. It seems very odd to talk about inequalities and not talk about graphs. So my focus for this week are those 5 topics, and they will tie in with, I hope you recognize that they tie in with the practice questions which we circulated, and there will be Emma will be circulating tomorrow. Thank you in advance, Emma. Emma will be circulating in tomorrow some questions, some practice questions, some warm-up questions for next week, thinking about graphs and including inequalities and completing the square. Slightly oddly, my next slide says in conclusion, you haven't just like dozed off for an hour and a half and it's now 4 o'clock. But I thought I might present the conclusion first, and then you can sort of see what I'm trying to exemplify through my examples. I do love a catchphrase. So I think this is my conclusion about year 12 teaching, that beginning of year 12 teaching. Unfinished business leads trouble ahead. So when you are teaching certain algebraic topics, or when you're sort of getting the students to kind of explore, even just practice certain algebraic techniques, you've got to think about how far do you need to go with it now to avoid trouble ahead in the future. So if you think about that example I gave you a few moments ago of the derivative of that curve, by the way, straight away, first problem number one is, well, isn't the answer y equals 1, by the way, because isn't the denominator the square root of x squared plus 1? So it just cancels x squared plus 1 over x squared plus 1. So first of all, got to deal with that issue. But how far in work on simplifying indices, how much work should you do, should you front load into year 12 so that you have finished the business and therefore you avoid or you reduce the trouble ahead in year 13. So it's about pushing further in year 12 than you think you need to avoid or to reduce the trouble ahead in year 13. Tactics versus strategies. So often students they think they're learning how to solve a type of problem, but all they're remembering is how to solve the particular problem. So they focus on the specific strategy for the specific problem, but they don't grasp the general tactic for the class of problems. And so as I'm going through my examples today, I will try and draw out that this is a specific example of a particular type of problem, of a class of problem, and therefore what's the strategy and what's the tactic. Desirable difficulty and productive struggle. They're two phrases which they're used a lot and they sound a bit cliched, but they're really good phrases. It's really good if they get stuck. It's really good if they can't do it. Particularly, well, it's even better if they can't do it and then they learn how to do it. So it's making sure that you are putting that productive struggle into your activities. And I hope some of the activities I share with you this afternoon will show you perhaps how I go about doing them and give you some ideas about how you might do so as well. Get the maths from them, asking them questions. Ask them questions to get the maths from them. Planning a lesson, I say to beginner teachers, planning a lesson is about planning a sequence of questions. It's not planning a sequence of statements. And I will use lots of my favorite questions throughout this afternoon. And at the end, I've got a slide, something like question bingo. You can tick off which ones I've used and see if you get the entire full house. And then I have accommodation rather than assimilation. That sounds like I'm being very, very unwelcoming I'm being very uninclusive of diversity. That's not what I mean. Accommodation rather than assimilation links to the work of Skemp, the education of Richard Skemp, and I'll come back to that at the end. And I think a lot of the problem is that, which I'll illuminate with Skemp's examples, a lot of the problem is that what students are doing is they are not expanding their understanding. They're kind of cramming more and more ideas into the same area of their maths brain, and they're not expanding their understanding. So they're assimilating, they're not accommodating and enlarging. And if you remember from your own training, Skemp's work, that'll ring a bell. If it doesn't, then I've got some examples to share with you a bit later on. We will have a coffee break at about 3:05, 3:10, or at least a leg stretch break, I promise. Okay, so let's get started then on the maths. So I think this is a really good example of unfinished business. So what do students learn at GCSE? Well, they learn how to factorize. What they come away with is they think what factorize means is the method of factorizing. So the most common one I hear from my students is they're told sort of something like you've got to make the sum equal 5 and the product equals -14, and then they sort of go, oh, what's that? That's 7 and -2, and so they write x squared plus 7x, take away 2x, take away 14, and so they write x plus 7, take away 2x plus 7, which is the same as x take away 2, x plus 7. Job done, move on. I meant to say, by the way, do please put comments in the chat if you want to. I'm keeping an eye on the chat. I won't necessarily answer things immediately. I'll choose moments to do so. Do put things in the chat, particularly if I get anything wrong, which is highly likely. If I make a mistake, please let me know. And if you've got any questions, then perhaps we'll have a bit of a question pause a little bit later on. You will get the slides afterwards. And one question, by the way, is what would happen if we did it the other way around? You know, what would happen if I did x squared subtract 7x plus 2x subtract 14. Would that give me a different answer? No, but it's probably worth their checking it. A lot of students I work with, that's what they think factorizing is. So they think factorizing means find two numbers that add to make, in this case, 5 and multiply to make negative 14. They don't think that factorizing is that rewrite as a product. So there's your first question. First question for your first lesson in September, what does factorize mean? And they will tell you how to do it, not what it means. They won't say it means rewrite as a product, rewrite as a multiplication, re-express as a multiplication. Why does that matter? Well, it matters because, unfortunately, it's not true that you factorize cubics by finding two numbers that add to make 3 and which multiply to make negative 14. And so their understanding of factorization is an example of unfinished business. They haven't got a full understanding, haven't finished their understanding of factorization at GC level, and so there's trouble ahead when it comes to factorizing cubics. Now, how do they factorize cubics? There are lots of methods of factorizing cubics. The one I teach, therefore the one I always advocate, is to represent it pictorially, to represent it as a rectangle, as an area. Sometimes people call it the grid method. Really, it's the area method. Let's just backtrack here. So what I mean by that, if you wanted me to factorize x squared plus 5 to the 14, I would draw my grid. I talk about farmers' fields. Here's my farmers' field. And I am going to have an x there, and they're going to have a negative 14 there, because I know that's a number and that's a number. So number times number equals negative 14. By the way, I expand in the same way. If you ask me to expand two brackets, I will write them as the margins of the grid and fill in the grid, and that gives me my answer. So I've done lots of expansion, so I know that I always get the number, the pure number, bottom right. And then I go, I just want to make it work. Well, I want to make it work. So what would do? Oh, negative 7 and 2. So I try negative 7 and 2. Oh, but that gives me negative 7 and 2x. That's not right. So let's just rub those out. Okay, like those. So let's try maybe 7 and negative 2. So that gives me 7x. That gives me negative 2x. Great, that's correct. So that's my answer. X plus 2, x plus 7, x subtract 2. So I expand brackets at GCSE using an area representation of farmer's field. I factorize using my area representation using my farmer's field, and I do the same thing for cubics. Now, obviously for cubics, you have to spot the first solution, so that doesn't change. So we think to ourselves, x equals 2, yep, because 8 plus 6 take away 14 is 0. So x equals 2 is a root. It's one of the roots, and therefore x subtract 2 is the factor. So that doesn't change. Therefore, x subtract 2 is the factor. Now, what a lot of books teach at this point is long division, and I don't find it very successful, and I don't like it because I think it doesn't connect back with what they should have been doing at GCSE. So I want factorization to be continuous from GCSE to A level. So I want to take the example, the method we use at GCSE, which is filling in the farmer's field, and apply it at A level. So how do I do that? So I draw my farmer's field. Now, since I want to make a cubic, I'm probably going to have a quadratic here. So there's my x and there's my subtract 2, because x subtract 2 is a factor. So what have I got so far? I've got x cubed and I've got negative 2x squared. Now I don't want negative 2x squared because there are no x squared terms in my cubic. So what could I do? Well, if I have a 2x there, then when I fill in the areas, that area will be 2x squared and that will be negative 4x. I agree talking about negative areas pushing it slightly. So I sometimes say sort of the area in inverted commas is negative 4x. I'm generalizing the idea of area. And that's looking good because they will cancel. And then I want 3x altogether. So I better have a 7 there because that will give me a 7x. And then it'll give me a negative 14. And then 7x take away 4x is 3x. Got that. And I've got negative 14. Fantastic, job done. So my factorization is x subtract 2. So my factorization is the same as x subtract 2, x squared plus 2x plus 7. Do you want to just try those two, or the last one, in the same way? Just have a go, a couple of minutes by yourselves, or if you're sitting around a table in a school, if you want to do it with your colleagues, just try to set those two in the same way, particularly if it's unfamiliar to you. So you've got to spot the factor. So you're trying to make the grid. You're trying to make the grid in both cases. And you do need to spot the first factor. What's the magic number that when you substitute it makes the expression equal 0, and then filling in the rest of the grid from that. So I'll just give you a couple of minutes to do that, folks, and then I will start writing on the screen, and you can have a look and see if you agree with me. So first of all, I'm going to think of the magic number, which is also 2. So x equals 2 is a root of this expression. So x subtract 2 is a factor of the expression. So it starts off in the same way. And then I'm just going to fill it in a column at a time. So you'll see, obviously, it's very similar. So that's what I got for my grid, x subtract 2, and then x squared plus 2x subtract 15. So, and then I'm essentially going to stop there and move on. But of course, first of all, I'm just going to check about the quadratic. Does the quadratic factorize? So x subtract 2, and it does x plus 5, x subtract 3, which again, I could do with a grid, but I've slightly run out of space. Suggestions for the second one? Did people get a factorization by any methods? I'm hoping that you did it by grid, but if you have a factorization to share, then please do share it. I agree with you, Phil. X subtract 3 is a factor because that gives us 27, subtract 18, subtract 9. So x subtract 3 is a factor. I absolutely agree with that. I'm going to move my grid down. So move it down here. So x subtract 3. And then we've got x squared plus 3x plus 3, which I agree with. Okay, so thank you, folks. So should have got x squared plus 3x plus 3. Because obviously I started with expansion and built it backwards. What does that look like in terms of the grid? So there's an x squared there because that gives x cubed, take away 3x squared, and then plus 3x gives us plus 3x squared, take away 9x, and then plus 3 gives us the plus 3x. We want to get negative 6x overall, and it gives us the negative 9. So the diagonals all cancel, and we're left with what we want: x squared plus 3x plus 3. Thanks, Phil. Thanks, Leah. Thank you. I appreciate you. And thanks, Constance, as well. Thank you for sharing that. So hopefully you've got a grid which looked like that. If you're still thinking about the grid, then I think it's a really good method to come back to. It just as a little kind of extension, we can also do remainder theorem questions. Now, I agree that by far the most efficient way of doing this question, the remainder theorem question, is to use the remainder theorem. I completely agree. The best thing to do is substitute negative 2 to the 4 plus 3 lots of negative 2 cubed plus 5. So 16, take away 24 is negative 8, plus 5 is negative 3. So in terms of the exam, absolutely the thing to do is substitute in and use the remainder theorem and get the answer negative 3. But just quite nicely, what happens with the grid? What happens when we try to factorize it? Where does the remainder come from when we try to factorize it? So we are factorizing by x plus 2. Now I agree x plus 2 is not a factor, but that's what we're trying. So we're going to have an x cubed there to give me an x to the 4 and a 2x cubed. Now altogether I want 3x cubed. So I better have another x squared there, and that gives me an x cubed and a 2x squared. So I've got the right amount of x to the power 4 and the right amount of x cubed. I don't want any x squareds, so let's subtract 2x there. So that gives me negative 2x squared, negative 4x. I don't want any x's either, so I better have a plus 4 there. So that gives me a plus 4x, and it gives me an 8. So have I got the right amount of x to the power 4? Yes. Have I got the right amount of x power 3? Yes. Do the x squared terms cancel? Yes. Do the x terms cancel? Yes. And what am I left with? I'm left with 8, but I don't want 8, I only want 5. And so I need my remainder of negative 3 and subtract 3. Because my factorization with x plus 2 ends in an 8, and I don't want an 8, I want a 5, so I need to subtract 3. So subtract 3 is the remainder. So we can see how the remainder comes out from a nearly factorization. X plus 2 is not a factor because it doesn't equal, the expression doesn't equal 0 when you substitute it. If you treat it as a factor, you get a nearly factorization, and to make it a really factorization, you have the remainder. Well, it's not really factorization, I suppose. To make it a nearly, to transform it from the nearly factorization to the correct answer, then we have to subtract through the remainder. Great question from Chiswick School. Okay, so if it's 12x cubed, the method is the same, it's just fiddlier. It's just more complicated because you have to consider other options. So if this had been, say, 4x cubed, we'd have to try things like x and 4x squared and 2x and 2x squared. So it becomes more complicated, I agree. And there comes a point maybe where it becomes inefficient. But certainly as a bridge from GCSE to A-level, I think it's a really powerful bridge. Thank you, Sudha. Great question. I think so, yes. That's why I do it, because this to me is connecting the fact that factorization is emphasizing the fact that factorization is the inverse of expansion, it's the inverse operation, the reverse process to expansion. So with expansion, I have the margins, I fill in the grid. With factorization, I fill in the grid and I find the margins. So I think it gives a much better understanding because you're connecting factorization and expansion. Long division, synthetic division, is just a procedure. It's just an operation. It's also quite a hard one as well. It's quite a fiddly one as well. So to me, absolutely. But then I've been thinking about this for a long time. So it's something you need to come back to again and convince your students of again and again and again. Thank you, Jessica. Good. Thank you, Jessica. Good. I'm glad to know that you think it works for you. So if it's new to you, maybe something worth trying. Okay, so factorizing, then factorizing more generally. So I think this is a really good example of tactics and strategies. So strategy, simplify, expand the brackets, right? So 81 lots of x squared plus 2x plus y squared and 16 lots of blah, 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 blah. So obviously you can expand the brackets. So the strategy is expand the brackets. And here, what would I do down here? I'm gonna have a 3x3 grid down here, aren't I? 3x3 grid down here. X subtract 3 plus root 2, x subtract 3 subtract root 2. Got 9 terms to fill in. It'll work. It'll get fiddly, but it'll work. So I can definitely do that. So strategy, expand the brackets, collect the like terms. That's not very efficient. So what's the general tactic is look for structure. Is there some structure here that I can see and exploit? What am I seeing? I'm seeing a square and a square. I'm seeing a subtraction sign. That to me says the structure is the difference of 2 squares. So how do we get our students to recognize the difference of 2 squares? Because we describe the structure to them. If you have got something squared, take away something squared, you should think of it as the difference of two squares. Now, of course, it works really well here because not only have we got a square power, we've got a square coefficient. So obviously, it'd be slightly harder if this was 5 and 7. But the fact it's 81 and 16, these are square numbers. So we really have got something squared, take away something squared. So we really have got the difference of two squares. So we don't want to follow the strategy of expand the brackets and collect the like terms. We want to follow the tactic of look for the difference of two squares. So what are they? So it's 9x plus y all squared, subtract 4x subtract y all squared. And then we need to think, well, what do we do with the difference of two squares? What is the rule for factorising? What is the structure of factorising the difference of two squares? Answer, it's the unsquared thing plus the unsquared thing. The unsquared thing subtract the unsquared thing. Sure, I could express that more mathematically if I tried. So the answer, factorisation has got to be 9 lots of x plus y plus 4 lots of x subtract y multiplied by 9 lots of x plus y subtract 4 lots of x plus y. Sorry, plus there. That has to be the factorisation. That has to be what you get by simplifying it, because we've got the two squares. So it's the first expression squared, so subtract the second expression squared. So it is the first expression plus the second expression, multiply by the first expression, subtract the second expression. That is the structure. So we take a step back and look and recognise what we've got here. So to finish it off, I've got 9x and 4x is 13x, and I've got 9y take away 4y is 5y. And then I've got 9x take away 5x is 5x, and I've got 9y plus 4y is 13y. So that's my answer. Now, I suppose I can expand the brackets. I could expand the brackets, and I could say it's it's 65x squared, and it's 65y squared, and it's 169 and 25, which is 194xy. But why do that? I factorized it. Factorize it is very nice. Factorizing it is often more useful factorized than expanded. So I've taken a step back and I've looked to recognize the structure. Hint, can we see the same thing in the next example? Can we see the same structure in the next example? Or can we see a structure in the next example? Why do I not need a 3x3 grid to expand these brackets? Any observations, suggestions in the chat? By the way, totally coincidentally, we've paused at my favourite time. It's my favourite time because 38 squared is 1444. 38 squared is the first square number that ends in 3 4s. And so, honestly, it's true. I've changed now. Sorry. But it's honestly true. I do get very excited at 1444 every day. Just before 2:45, I get very excited because it reminds me of my favourite square number. Right, sorry, folks. So can we see any similar structure? Can we see anything difference of two squaresy in the next example? Can we see something plus something, something take away something? Yes, so the first bracket, oops, sorry. So the first bracket I could rearrange like that, okay? I was trying to make it even more straightforward than that, actually. I was looking for, so does that help? Yeah, exactly. So just sort of let A equal X. Sorry, I was looking down at my screen when people suggested. Thank you, Johnny, and thank you, Chiswick School. Thank you, colleagues there. The structure we've got is x subtract 3 plus root 2, x subtract 3 subtract root 2. And so the expansion has got to be x subtract 3 all squared subtract 2, root 2 all squared, which is what Johnny's put in the chat. Thank you, Johnny. Thank you, Rich Kellenfeld, in the chat for that. And thank you, Chiswick. So the structure is, sorry, folks, my iPad's just shut down for, I'm just going to pause the, I don't understand, folks. Why don't we just take a 5-minute break? Well, I might need to restart my iPad. I'm a little confused and a little flustered. So I'm going to stop the recording, and then I will. No, sorry. I shall pause the recording. So as we were saying, the structure is x take away 3 plus root 2, x take away 3 take away root 2, and therefore it's the difference of two squares. And therefore it has to be that we get x squared, take away 6x, plus 9 take away 2, i.e. plus 7 as the final answer. Now, clearly, if we'd filled in our 3 by 3 grid, we must have got that, but you can just imagine all the potential for problems, all the potential for going wrong. So yes, the strategy often is expand the brackets, collect the like term. The tactic is take a step back and look for structure. So thinking about factorizing. So we do lots of factorizing with quadratics and cubics with positive integer powers. Do lots of factorizing. Do we do enough factorizing with negative integer powers? Probably not, is the honest answer. Now, of course, in many ways, the best way to do this sort of question is not to use the integer powers, the negative powers at all. Often the best thing to do is just go, right, okay, what is this? It's 4 over x squared, subtract 1 over x cubed. Now, it's really important to do lots of this because, of course, this will expose all their misconceptions. So is it 4 over x squared? Is it 1 over 4x squared? Is it 16 over x squared? And then is it 3 over x or x over 3? Or, there are all sorts of hideous reinterpretations of the negative power. So it is actually really worth converting backwards and forwards between negative indices and fractional representations, because you need to check that they can do that confidently and fluently. And so once we've got that, then how do we factorize? Well, they will. I think you will find that they're so used to, when you've got an x squared and x cubed, you take out the factor of x squared, that they'll try and do the same thing. So they hopefully will realize it's a fraction, and then so take out the factor of 1 over x squared, and then, well, what's that? Is that 4 over x? Is that 4 over 4? Is that what's that? And then what's happening there? So obviously it would be much better if actually what they did was they factorized by 1 over x cubed, and then that would be a 1, and then what would that have to be there? Well, that's where the productive struggle comes in. That's where the desirable difficulty comes in of working out that. Of working out, okay, yes, there's another quick glitch of working out that needs to be a 4x there. And how do I know that's 4x? Well, because I'm sort of thinking I've got x over x cubed, which cancels down to 1 over x squared. Now, I'm not for one moment saying that's easy. That's the point. That's the desirable difficulty. That's the productive struggle. And then once they've done that with writing the negative indices as fractions, then can they do it using only the negative indices? So what is the common factor here? If I write x to the negative 2 as the common factor, then obviously that's 4, but what's there? So what do I multiply x to the negative 2 by to get the answer of x to the negative 3? And that's the idea of using the laws of indices backwards. So probably most of your A-level students, they're probably perfectly happy with x to the cubed, x to the 3 times x to the 5 is x to the 8. How much of x to the 7 times what have they done to give x to the 9? And certainly how much of x to the negative 3 times what is x to the negative 5, say, have they done? So if you like, that's the forwards way of using the laws of indices. When I'm multiplying bases, the same base raised to different powers, I can add the power, I can add the indices. What about going backwards? What about unpacking? What about factorizing using indices, using the laws of indices backwards? So if they have the factor of x to the negative 2, working out what goes there is not easy. It's productive struggle. And of course, they might want to say, well, what happens if we take out the factor of it next to the negative 3? So if I write x to the negative 3, well, obviously that's going to be a 1, but then what goes there? And are either of those the same as that? So doing the same question 3 ways, working with the fractions, which is by no means straightforward, and then working with the negative indices, which is definitely not straightforward, and checking the answers give the same. And so something sort of similar here. So obviously I could write it as 4 root x subtract 1 over root 4x. Is that right? Or is it 4 root x in the denominator? Is it 4 over root x? Or all that complication? And then what would that be as maybe as a common denominator? Or maybe so how might I simplify that? But then alternatively, if instead I try to factorize it, well, is there a 4 as a common factor? I can see a 4 twice. Is there a 4 as a common factor? Is there an x to the half as a common factor? Is x to the negative a half a common factor? If I do, you know, obviously if I choose, let's ignore the 4 for the time being, that will be a 4 there. What's going to go there? And then actually also what's there? Is it 4? Is it a quarter? Is it a half? Is it 2? So completing those brackets, you know, the grappling with that, the productive struggle with that, doing that now in year 12, but not now in year 12, so at the beginning of year 12, you know, you can see where all this comes from. This comes from derivatives. This could easily be some sort of solving a turning point equation, and really understanding what do they you understanding what do they understand about working with negative and fractional indices. So factorize something like this. Okay, now when I've set questions like this in the past, what the students often say is, oh yeah, well, you multiply both sides by. So if they're quite confident, they'll kind of write this as 4 over x squared, subtract 1 over x, subtract 3. And then they'll say, I'm going to multiply both sides by, and they'll write 4 subtract x, subtract 3x squared. I'm going, what? How can they be equal? And when you say you're multiplying both sides by, what is the other side? There aren't 2 sides there. So we don't want them. We certainly don't want them doing this, multiplying both sides by when there aren't 2 sides. I suppose they could introduce a y or perhaps an e for expression and then multiply both sides by. But that's not what we want them to do. We want them to recognise the structure. So what is the structure of what we have here? Well, it's 4 over x squared, subtract 1 over x, subtract 3. That's a quadratic. It's a quadratic structure. It's 4 lots of 1 over x squared, subtract 1 lot of 1 over x, subtract 3. So it's a quadratic. So it factorizes like a quadratic. So it factorizes into 2 brackets, assuming it factorizes at all. And then we just try it. And obviously you can do this by saying, well, I want the sum to be -1 and the product to be -12. Or you can use a grid, or you can use trial and improvement. But what we want to come to realization is that when we factorize it, it is going to be 4 lots of 1 over x, and then 1 over x, and then a +3 and a subtract 1. I'm not saying that's obvious. That takes time to get there. But in the same way, if it was 4m squared, subtract m, subtract 3, we could factorize that. We can factorize this. Now, sometimes people like to do that. They like to substitute a letter for the 1 over x. That's fine. But it's even better if you can get them to think in terms of 1 over x, get them to see the structure of it being quadratic, and therefore to factorize like a quadratic, it's just going to be 1 over x's rather than x's. But everything else, 3 of those, take away 4 of those, gives me -1 of those, and 3 times -1 gives me -3. So it works. And then same sort of thing here. So 1 over 4x squared, subtract 1 over 4x, subtract 3. So it's a quadratic. It's sort of 1 over 2x squared, and then that's 1 over 4x, and then that's subtract 3. Well, maybe then it's going to be 1 over 2x. Oops, sorry, close my bracket a bit too quickly there. So it's going to be 1 over 2x, and then 1 over 2x. And then can I make it work? Well, if I have, say, a 3 and a 1 there, that gives me 3 over 2x, take away 1 over 2x, which is 2 over 2x, which is not quite right, therefore. That should be a plus, and that should be a subtract. So it's -3 over 2x plus 1 over 2x. And that's not right either. Okay, so so maybe it's not going to work with 1 over 2x. Maybe it needs to be maybe it needs to be 1 over 4x and 1 over x. So I forgot. Sorry, I forgot it was 1 over 4x. I thought it was 1 over x in the middle. Sorry. So ... Come back to that later. If I'll leave you to sort that one out yourself. I think it factorizes. I'm sure it factorizes. But that's the point. That's the productive struggle. That's the desirable difficulty. That's where the learning takes place. I completely forgot there was a 4 there. I'm absolutely sure it was 1 over x. So it's a quadratic, but don't give them the shortcut of multiply both sides by. Make them confront the difficulty of treating it, of factorizing as a quadratic in 1 over x. Simultaneous equations. So simultaneous equations at GCSE, how do they solve these? Well, hopefully the first one, they originally would say, oh, what could I do? I could multiply the first equation by 3 and the second equation by 2, and then possibly add or subtract. What tends to happen though is that they then learn about substitution. So they then learn that y equals x subtract 4 and substitute it in, and then they forget to do that. They start forgetting about that. So having learned a really good method of elimination, I find particularly higher attainers, particularly students with high grades, they just forget about it completely. They just don't want to do elimination any longer. They always want to do substitution, even when that's spectacularly inefficient, as we shall see in a moment. So actually, the problem is they've not been taught there are two methods, or they've not been taught that they've not been reinforced there are two methods, and which one you use depends on the context. So here you see, these all look, these look really complicated. Oh, they've got quadratics. Oh, I know what I do with quadratics. With quadratics, I have to substitute, don't I? Because they've done lots of ones like that with linear and quadratics. Sorry, like that with linears and quadratics, where substitution is a good strategy. So they come to this one with quadratic and quadratic, and they think, I must do the same thing. I must substitute. No, it's just a simultaneous equation in x squared and y squared. It's just the same. In fact, it is exactly the same, you may notice, as the previous question, the first question. I've just changed the letters. And so whatever method you worked best there, i.e. elimination, is the same thing here. So multiply by 3, multiply by 2, and subtract and solve for y squared, and then obviously go on and then solve for y, and then solve for x squared. Similarly here, and you had one of these in the practice questions with surds. Putting surds in makes no difference to the structure. The structure is still eliminate. So what might I do? Well, I might multiply the first one by root 2, because that would give me a root 6. Yeah, and actually I might leave the second one alone. Yeah, multiply by root 2, and then I'm probably going to add them, I think. I may well add them at this point, because I'm going to get root 6 and a negative root 6y and positive root 6y, so I'm going to add them together. So just that tiny sort of extension of using surds as the coefficient will really focus their attention on the method and the tactic of elimination. And then here is that mechanics question from earlier. You may remember it. That was the setup. There was my 5G, and there was my 20 newtons, and there was my string, and there was my string. And so those are going to be my simultaneous equations, particularly if I put the 20 newtons on the other side, or change letters around. So I want there, s cos 70 plus 20. So how do I solve those? In the same way that I solve all the others, by elimination. So I'm going to multiply, say, the first equation by sine 40 and the second equation by cos 40. Now, those coefficients are not going to be nice coefficients, but they are just coefficients. So all these equations are elimination equations, even though they look so different, because the tactic is make two coefficients the same if I can, and then add or subtract accordingly. So it's recognizing, I say, that underlying structure, not the surface detail of this one's got squares in, this one's got surds in, this one's got trigonometry in. They're all elimination. So do you want to sort of think about these? How would you go about solving these? What would you do? Perhaps if you're with somebody, chat to somebody next to you. If you want to put something in the chat, that'd be great. But you may not wish to. That's fine as well. So why don't you let's take a couple of minutes to think about these. Let's take 3 minutes to think about these. How would you solve them? If you want to solve them, by all means do. How would you go about doing so? Good question, Sudha. Basic answer is as late as possible. Because as soon as you use calculators, they will stop learning a method. So as late as possible, I would say. I'm very anti-calculator. So 3 minutes thinking by yourselves. How would you go about solving these? How do you think your students would? Would they do it in the same way? How would you go about solving them efficiently? So if you're sharing ideas with colleagues next to you, then by all means, please do put your sort of combined thoughts in the chat, or if you're by yourself but still want to share your thoughts, that would be lovely. If not, I shall share some thoughts in a couple of minutes. Now, obviously, all of them I can make X the subject or Y the subject and substitute. So why do I not want you to say that? Well, you can do that. Any thoughts about why not to do that? Is there any reason why we perhaps might want an alternative to make X subject or make Y the subject and substitute? In your experience, why what can go wrong with that? For the first one, what Y equals or X equals, which would you make the subject? Almost like a little vote in the chat. Tell me X or Y for the first one. Yeah. Okay, I think I would do the same thing. So guess why? Why do you want to avoid X equals? What's wrong with X equals? Just need a fraction, right? Okay. So so I think with the other two, then the problem with making either X or Y equals the subject is that you're going to have fractions. You have lots of fractions, then you can start squaring things with fractions, then you have all the whole world of pain with fractions. But that idea of you make Y the subject and you substitute, and you make X the subject and you substitute is very ingrained from GCSE. That's what, and there's another example of unfinished business. They've learned a method which is make Y the subject, substitute, make X the subject, and substitute, and they haven't taken a step back and thought, is that always the right method? When is that the right method? Are there ever alternatives? Alternatives for the second one or the third one? Don't mind. Any suggestions from people? Any thoughts about what you might do to avoid fractions in number 2 or number 3? I'm not against making 2Y the subject. It's making Y the subject that I'm quite keen to avoid. So I'm perfectly happy to make 2Y the subject. And if people want to make a suggestion, that would be great. Oh yeah, I'm going to go with that, Rekha. Thank you. Yes, so I'm going to square this, and that's going to give me 4y squared equals something. Not nice, but certainly 4y squared. And then what am I going to do? I'm going to take this equation and multiply it by 4. Multiply it by 4. So I'm going to then have 4x squared plus 4y squared is 52. And now I am going to substitute. I am going to substitute 4y squared for that, but I haven't got any fractions. So I'm going to scale up rather than scale down, okay? So make 2y the subject, make 4y squared, therefore the subject, and then substitute 4y squared into a transformed, a scaled up equation rather than a scaled down equation. So thank you, Rekha, for suggesting that pathway. And same thing with the next one. So what I do with the next one, just for a bit of variety, let's make 2x the subject. So I'm going to make 2x is equal to 12 plus 3y. So that gives me 4x squared is 12 plus 3y all squared, which isn't very nice, but at least it's all whole numbers, at least integers. Now what am I going to have to do? We've got 4x squared, and so here, what could I do? I could multiply this equation by 4, and that will give me 12x squared plus 8y squared is 140. And then I can multiply this equation by 3, so 12x squared is 3 lots of that square bracket, and then I can go from there. Okay, so now I can substitute that expression for 12x squared. Now, I'm not saying that's easy. I've still got a big quadratic with big coefficients, but at least they aren't fractions, at least they're whole numbers. So this idea of make x the subject, make y the subject is quite a limited, quite a narrowing response to simplest equations. Keep in mind the idea of elimination, which is try and make the coefficients the same. Now, when we've made the coefficients the same, we might be able to add or subtract, or we might have to substitute, but it's that focusing on scaling up. What did we do at the very beginning in kind of year 9? We scaled up the coefficients to make them the same. We can still do the same in year 12, in year 13. I was going to leave you those two to do with the coffee break, okay, and think about how you would go about doing those. You'll get the slides, you can play around with those by yourselves and see what happens. This was going to be our coffee break. I'm a bit fussy about my coffee. I do like coffee paraphernalia. I do like a messing around, making a cup of coffee. So I was going to go and do that for 10 minutes, but I'm not now. So I hope you're okay to continue. I hope that's all right. I'm sorry we broke slightly earlier than would have been ideal. So algebraic fractions, but more generally then. We've talked a bit about negative indices, so lots of work to be done here. What does this mean? Is it 1 over 2x cubed? Is it 6 over x? You know, there's all sorts of misconceptions that we can draw out here, and actually it's really worth doing that. It might be worth trying to sort of write out what are all the possible wrong answers people might come up with, and then can we explain why each of them is wrong? So sort of an activity, almost a bit like a treasure hunt, where you sort of say, right, okay, let's think of all the different plausible but wrong answers. So 1 over 2x cubed, 2 over 3x, 1 over 6x. You know, all the 2's and all the 3's and all the various places. So draw out all the wrong answers and then diagnose why each of them is wrong. What's wrong with 2 over 3x? What's wrong with 1 over 2x cubed? What's wrong with 1 over 2x in brackets all cubed? Why are they all incorrect? And try to explain the what it's not as well as what it is. So kind of let's kind of go through the what it's not options before we get to what it is, which obviously is 2 over x cubed. Sorry, yes, that's right. 2 over x cubed plus 3 over x cubed. And then I bet they make a common denominator. I bet they make a common denominator of x to the power 6, because they've kind of internalized the idea that what you do is you make a common denominator rather than you look to see, is there a common denominator? So I bet straight away many students would write that as well, something over x to the 6, and then not be totally sure what to do next at that point. Then same sort of thing here, but of course now we do need to think about a common denominator. So what's the same, what's different? So in terms of the question design, what have I changed? I've changed one thing. I've changed the second index of -3 to an index of -2. I've made one tiny change, and that's made it a completely different question. Okay, perhaps not completely different, but a substantially different question. So that's what I mean by this idea of question design. A very small change to the question, and obviously you can see what I've done for the next one is I put in some brackets. So now I now have got 1 over 2x all cubed plus 1 over 3x all squared. And so that progression, imagine using those in class. Think what's understanding and probably also misunderstandings, conceptions and misconceptions that would draw out, and just those small changes. What have I changed? What's the effect of the change? My absolute all-time favorite question is what's the same? What's different? Closely followed by what do you notice? So what's the same, what's different? What do you notice? Are they seeing the difference between -3 and -2, between the brackets and the no brackets? And can they tell you what that means, what the effect of that is? So trouble ahead is that. Now that, by the way, is the derivative of the function we met earlier. So assuming I've differentiated correctly, that quotient differentiates to that. So if I want to find some turning points, say, I want to make that equal to 0. Now I can't do that unless I've done lots of those sorts of questions in year 12. So we think about algebraic fractions, and we have to think about having integer powers. So we think about algebraic fractions which look like that. Do we think enough about algebraic fractions with non-integer powers? So recognizing that this is root of x plus 1, subtract 1 over root of x plus 1. And now what do? What's an algebraic fraction? So we do what we always do. We find a common denominator. So that's over 1. So my common denominator is going to be over root of x plus 1. And then what goes there? Well, what have I done? I've multiplied the denominator by root x plus 1. So I multiply the numerator by root x plus 1. And I do often see students writing that and then just like going on to the next question, like, no, the square root of something squared. What is the square root of something squared? It's the thing. And so recognizing that this therefore gives us x over root x plus 1. So simplifying algebraic fractions, these are algebraic fractions, they're fractions of algebra. So simplifying algebraic fractions, but also involving roots, involving surds. Or perhaps here, just more generally factorizing. So lots here to draw out. What happens to the 9? What happens to the 4? You know, is it 9 lots of x plus 1 to the 3 over 2? Take away 4 lots of x plus 1 to the half? No. Why is it not? That should be 2. What should that be? That should be 27. Well, why? Can we explain where that's come from? And now what do? Well, we haven't got any fractions here, so perhaps algebraic fractions. Perhaps this is on the wrong slide. It started off as a fraction, then I changed it. So we haven't got any fractions here, but can we factorize it? Have we got any common factors? Well, that goes back to what we talked about earlier. There is a common factor of, say, x plus 1 to the half, but then, well, that presumably is going to be 2x there. Then what goes there? What do I multiply x plus 1 to the half by to get x plus 1 to the 3 over 2? So what to the half times is my question. Again, it's going backwards with the laws of indices. Is it 3, say? That will come up as a very common wrong answer. It's 3, because 3 halves make 3 1/2. They see 3 over 2, they see a half, they think, oh, right, I've multiplied by 3. But if they're not doing lots of that sort of in the beginning of year 12, if you don't finish off that business in year 12, then they're never going to do that successfully in year 13, because they're just not going to know what to do. They're not going to sort of go, right, what have I got here? I've got common factors of 2 and x and something to do with x to the 4 plus 1. So I've got a common factor of 2 and x, and then x to the 4 plus 1 to some power. Now, what would be good? I should take the smallest power, and the smallest power is negative 1.5, not 0.5, negative 1.5 is the smallest power. And so I'm going to have to the power 1 there. And then I'm going to have a 2x squared. No, sorry, I don't need a 2, do I? I'm just going to have just an x squared and then the x squared plus 1 there. So I've taken this x to the, I've taken x to the 4 plus 1 to the smaller of the 2 powers as the common factor. So then I've got to work out that that is the power of the other factor, sorry, the other term, sorry, in the second factor, to take me back to what I want, which is the power of negative a half. Now that's really hard in the middle of an A-level question. And if you haven't done lots and lots of practice, I always think of people like Michael Jordan, the basketball, talk about the thousands of hours of practice, the thousands of shots he missed. You're not going to do that in the middle of an A-level question if you haven't done lots of things like that, or certainly like that, in year 12. Speaking of algebraic fractions, so what would they do here? Well, the autopilot is to write this as x to the negative 4, 3x squared, take away 4x to the 5, and then expand the brackets. So it's 3x to the negative 2 because I'm adding the indices, and then it's 4x to the negative 1 because I'm adding the indices. But then what? If I want to try and solve this as an equation, then I've got all these negative indices. So is there a way of avoiding the negative indices in the first place? Yes. I call it, I don't know if this is an official term, I call it splitting the numerator. And when I say I call it, I mean that's what we call it at King's. I'm not sure who thought of it first. I very much doubt it's original to King's. I very much doubt we thought of it. So splitting the numerator, so rewriting this as 3x squared over x to the 4, subtract 4x to the 5 over x to the 4. And then it's just much easier to cancel down the fractions. And seeing that as 3 over x squared and then 4. Why did I get -1 there? Sorry, folks. That should have been a positive one, shouldn't it? Sorry, because that was power 5, power -4. And so exactly that should have been 4x. Sorry, if someone told me that in the chat, I apologize for missing that. Sorry, folks. Sorry, that should have been power 1 because -4 and power 5 gives me a power of 1. So now, if I want to say to integrate that or differentiate that or solve an equation, that seems to me it sort of exactly took the words right out of my mouth. This is so much better for integration. Thinking, okay, right now, how do I integrate this? Well, first of all, I split the numerator. Particularly say something like this next one, absolutely. Just duplicate the slide, clear some space. So for the second one, what's my split going to be? It's going to be 4x over 3x plus 5 over 3x. So it's going to be 4x over 3x plus 5 over 3x. So it's 4/3 plus 5 over 3, 1 over x. So then let's say I'm integrating it. Well, great, because I can integrate 4/3 and I can integrate 1 over x, I hope, and the 5/3 doesn't, just a factor. So integrating that is really hard. Integrating that is much more straightforward. Hence, exactly, I completely agree with you, so thank you. It's exactly got those links. And same thing here as well. So integrate that. Really? Do I have to? No, the first thing you do is you split the numerator and think about the powers. So it's 2x to the 2.5 over, well, root 3x to the 1.5, and then 9x over root 3x to the 1.5, dot, dot, dot from there. Absolutely, thank you, Yuvraj. Absolutely, it's about coherence. It's about linking apparently different aspects of the syllabus, of the content, but also over time. So this messing around with indices, this all goes back to GCSE, where you need it is in the middle of year 13. Thank you, Yuvraj. Now, I can't resist just talking about these ones quickly. Think about higher retainers, or if you're teaching further maths in particular. So just a little side, if you just give me a little sideline for teaching sort of the students aiming for the A stars or for the mathematicians. What did you hear? How do you split the numerator here? Well, what I would do is I would say this is the same as x squared subtract 1 plus 1. I hope you agree with that. And then I would split it as x squared subtract 1 over x plus 1 plus 1 over x plus 1. Because that simplifies, because the numerator is the difference of two squares. So the numerator is x subtract 1, x plus 1. And so that will simplify to x plus 1. Sorry. X subtract 1 plus 1 over x plus 1. So I split the numerator by putting in some more terms and taking out some terms. So I almost make the numerator more complicated so that I can split it. And then same thing here. So how do I integrate that? Well, first of all, I split the numerator. How do I split the numerator? I'm going to think of it as x squared subtract 1 plus 2 over x plus 1, and then I go from there. And then the last one, I'm going to think of this. So what do I want? I want an expression on the numerator that will cancel with the x plus 1. So if I've got x squared plus 3x, it would be good if I had plus 2 then take away 2, because that factorizes into x plus 1, x plus 2, and therefore the x plus 1 terms will cancel. When I split the numerator, I will get x plus 2, subtract 2 over x plus 1. Now that is incredibly useful in graph sketching and further maths, incredibly useful for some of the harder integration questions in single maths, but just generally as a way of practicing factoring, as a way of practicing quadratics, a way of getting to make some decisions. It's not it's not an automatic procedure. How do you change x squared plus 3x? You've got to add something and take away something. What's the right thing? There's lots of choices. I suppose could have done take away 4. What would that have given me? That would have given me x. Yeah, that would have been interesting. Would that have worked? Because then I would have an x plus 1 x. No, because that would give me negative 3x, not positive 3x. No, that's not going to work. Okay, so x squared plus 3x plus 2 works well because it factorizes into x plus 1, x plus 2. And then when I split the numerator, the x plus 1 term in the numerator, sorry, x plus 1 factor in the numerator and the x plus 1 factor in the denominator will cancel. So splitting the numerator is a really nice activity particularly for higher attainers. Okay, so think about indices and logarithms. I love questions like this because it's just so tempting to write 6x to the 6, and it's just so tempting to write 6x to the 6. It's really strong to write that. Obviously that's wrong, so can they explain why that's wrong? One of the 6's is correct, one of the 6's is wrong. So can they convince you why it's 6x to the 18 and it's 6x to the 72? And then here, so again that wholesome practice, and you can see what I've done. In terms of that small step variation, what's the same, what's different? What's the same, what's different? What should we do first? Well, probably the first thing to do is to write these as separate fractions and then think about multiplying them and dividing them. What do we get here? We've got 3 over x squared divided by, it says quickly, putting the 2 in the right place, divided by 1 over 2x all cubed. So what do we do first? What do we do next? What do we notice? Well, again, the small changes. I've moved the brackets from one term to the other. I've replaced the multiplication with the division. How does that change things? How does putting the brackets in and taking the brackets out change those terms so significantly? That fine detail. What do you notice? In terms of numerical work on indices, and of course this is heading towards logarithms, in terms of numerical work on indices, I think we do a lot of, what's 8 to the 3rd, what's 8 to the 2/3, what's 8 to the negative 2/3, what's 8 to the negative 4/3. So we do lots and lots like that. And that's really important. It's really important that they can do that. But in the end, that is just apply procedure, square and cube root, or cube root and square, and remember to reciprocate. So they can read it term by term. So I've got a negative power, that means reciprocate. I've got a power of 2, that means square, and I've got a power of 1/3, that means cube root. So in some order, I'm going to reciprocate square and cube root. That's what's quite nice, of course. It doesn't matter what order you do it in; they're all interchangeable. So although it's not easy, it is just doing the same thing. It's following a procedure with simplifying indices. Does it test their understanding of indices, their conceptual understanding? Is it just developing their procedural fluency? And I would suggest that those questions, which I just rubbed out, are testing their fluency mainly. Something like this, I'm hoping, is better for testing their understanding. So if 2 to the a is 9 without a calculator, so with my no calculator symbol in the top right corner of the slide, so without a calculator, what does that equal? So what we want to realize is this is the same as that. I.e., again, it's the laws of indices going backwards. If I give you 2 to the a times 2 squared, probably most of the students would write 2 to the a plus 2. If I start with 2 to the a plus 2, would they rewrite it as 2 to the a times 2 squared, i.e. 9 times 4, i.e. 36? 2 to the negative a. Negative 9 is a really powerful answer. 2 to the a is 9, 2 to the negative a is negative 9. So obviously not. It's the reciprocal, so it's going to be a 9th. 2 to the half a, so 4.5. 4.5. Nope, because this is 2 to the a to the half. Again, it's the laws of indices backwards. They're probably pretty good at x cubed to the power 5 is x to the power 15, it's the going backwards. You tell me about x to the power 15. Oh, right, it's x cubed to the power 5. So 2 to the a to the half. So the square root of 9, the positive square root of 9, and so it's equal to 3. And then 4 to the a subtract 1. Where's the 4 suddenly come from? So it's 4 to the a divided by 4, because divide by 4 to the 1, we're subtracting indices, is the consequence of a division expression. So let's go back to the division expression. And then 4, of course, is 2 squared. So it's 2 squared to the a divided by 4, which is 2 to the 2a divided by 4, which is 2 to the a squared divided by 4. So is that interchanging from 2 squared to the power a to 2 to the power a squared. And that interchanging, requiring the intermediate step, using, of course, commutativity of multiplication, is where the challenge comes from. And that therefore gives us obviously 81 over 4, 20 and a quarter. Now, of course, really, this is a logarithm statement. So my next slide, of course, starts with a logarithm. If a is log to the base 2 of 9, that's the same statement as we had there. But I don't think they can do the logarithms until they've done lots of work like this on indices. Again, it's about unfinished business with indices. If indices are only treated as work out 8 to the 2/3 and simplify x cubed to the power 5, if they only apply the laws of indices forwards, that's unfinished business, causing trouble ahead when they come to work with logarithms. So lots of kind of work with things like that, so that when we come to logarithms, we need a model in our mind. So what does this mean? And I would draw it as a picture. To me, I think of this as a flow chart. This says to me that if I start with 9 and I log it, or I log the base to it, I get a. And then to go the other way around the flow chart, to go backwards around the flow chart, is the inverse operation, which is to exponentiate it. Now, obviously, that's not obvious. You have to explain what's meant by a logarithm. You have to do some practice first. But once they've had the definition of a logarithm, I think that's a very powerful way. That picture is a very powerful way of thinking about it. If I've got 9 and I log it, I get a. If I exponentiate to base 2, if I exponentiate a, I get 9. So that answer is 9 automatically. It's not 9 on a calculator. It's not 9 by working it out. It's 9 by definition. It's 9. I just realised it looks like an a. Probably should have chosen a different number, shouldn't I? So it's 9 by definition. If you start with a and exponentiate it to the base 2 in this context, you will get the answer at 9. And then similarly, 4 to the negative a, well, that's 1 over 4 to the a, and we've just done some work on 4 to the a, haven't we? So 4 to the a is 1 over 2 to the a squared, because 2 to the a squared is the same as 2 squared, 2 squared, i.e. 4 to the a, because of the commutativity of the multiplication. As we just saw back there, 2 squared to the a is 2 to the 2a, and 2 to the 2a is same as 2 to the a squared, because multiplication is commutative. The multiplication of the indices, sorry, the a times 2 and the 2 times a is commutative. So that gives us 1 over, and then 2 to the a is 9, so it's 1 over 81, 1 over 9 squared. And so this diagram, or this way of thinking, this cycle, if I log it, I get a value. If I exponentiate to the right base, that value, I go back to the number I started with. It's just like squaring and square rooting. It's exactly the same as 9 square roots to give 3, 3 squares to give 9. It's the same function and inverse function, operation and inverse operation. So once we're kind of really comfortable with the idea of interpreting logarithm statements back as index statements, also got the laws of logs. So obviously laws of logs need teaching, explaining, and exemplifying. But then can we use them? So what's log to the base 2 of 18? What's log to the base 2 of 18? Well, it's log to the base 2 of 2 times 9. So it's log to the base 2 of 2 plus log to the base 2 of 9. So using our laws of logarithms, so it's going to be 1 plus a. So log to the base 2 of 2 is 1, and log to the base 2 of 9 is a by definition. And so what about this? Well, this is going to be log to the base 2 of 8 subtract log to the base 2 of 9. So it's going to be 3. subtract A. And then that one I shall leave you to think about. I mean, we've done lots of work connecting 4 and 2, so you can see how that's going to work out. Perhaps just a couple of minutes by yourselves on those. So A is a half log to the base 2 of 6. Simplify all of those, one of those, whichever one of those you feel like. I suppose I'm assuming some familiarity with laws of logs here. Definitely it helps if you realise that this is log to the base 2 of 6 to the half, i.e. log to the base 2 of root 6. So assuming you're familiar with laws of logs, then you might want to have a think about some of these. Which ones simplify to individual number answers, pure number answers? Which ones still have a log in the answer? Do all of them? Do any of them have a log still in the answer? Can I unlog all of them? What's the same? What's different? Just because I've written it a bit smaller and floating in the air, why does that make such a difference? Really happy for people to suggest answers in the chat if they wish to for any of them. I suppose we call them one, two, three. People want to suggest answers, that would be great. A 2 root 6 suggestion from Johnny. Thank you, Johnny. I'm in agreement with that because it's 12 divided by, now what's 2 to the A? Well, by the same flowchart we had earlier, we had root 6 and then we logged it to base 2 and that gave us A. So if we exponentiate to the base 2, we must go back to root 6. So by definition, it must be 12 over root 6. And then, of course, I can rationalize the denominator. Multiplying both numerator and denominator by root 6 gives me 12 root 6 over 6. So I get 2 root 6. Yes, thank you. 3 over 2 for question 2. So I've got 4a. So 4a is going to be, 4a is going to be 2 log to the base 2 of 6, which is log to the base 2 of 36. So I've got log to the base 2 of 36 plus 1 over log to the base 2 of 36 subtract 1. Now, how am I going to deal with that 1? Well, that 1, for example, I could say is log to the base 2 of 2. So I could rewrite that as log to the base 2 of 2 and log to the base 2 of 2. And then again, using my laws of logs, I've now got log to the base 2 of 72 by multiplying the arguments over log to the base 2 of 18. Log to the base 2 of 18. Can I go any further with that? Constance, sorry, I hadn't seen your answer. Constance, do you want to explain what you did next in the chat or out loud if you want to? Sorry, I didn't see your answer there. Sorry, Constance. Oh, you made an error. Oh, okay. Sorry, I wasn't trying to. Sorry, I wasn't trying to embarrass you or draw attention to you. Sorry, I was interested in know your thinking. Okay. So the question is, can we simplify this any further? Well, I mean, we could definitely do something with it because of course 72 is 4 18s. Ah, no, exactly. 2 to 5 is not 36. 2 to 5 is 32. Yes, exactly. Well, I didn't wonder where you got the 3 over 2 from. I was just thinking it through while I was talking to you. Okay, so what the students would often do is say, well, look, that is 4, 72 divided by 18 is 4. So they're going to write log to the base 2 of 4, which is 2. And so why is that not the case? And then here, well, what have we got? We've got, again, this is the same sort of question that we had before. We know that 2 to the a is 6. We know that, sorry, root 6. We know that 2 to the a is root 6. Any suggestions for the third one, by the way? Any suggestions for the third one? 2 to the a is 6. Sorry, it's root 6. And so 4 to the a. Thanks, Rekha, for making a suggestion. So 2 to the a is root 6. And so 4 to the a, well, again, it's the same argument about 4 to the a is being 2 to the 2a. So how do I get there? I'm going to square both sides, because that's going to give me 2 to the 2a, and 2 to the 2a is 2 to the 2, which is 4 to the power a. So 4 to the a is 6. So I'm going to get 6 plus 1 over 6, and then 6 subtract 1 over 6, and then I'm going to go from there. 37 over 35, I think I'm going to get as my final answer, 37 over 35. So lots of playing around, substituting logarithms and index statements, indices into effectively log statements. Laws of logs both ways. So if I give you a value, can you unpack it and use the laws of logs in a constructive way? Rekha, no need to worry at all. No need to say oops. Don't, you gave me an answer, which more than anyone else did. So thank you for doing that. I hope you can either see now or see later what mistake you made. Of course, possibly I've made a mistake as well. That's always the other possibility. So I've got 2 to the a is root 6, and therefore, if I square both sides, that does give me 4 to the a, gives me 6. So I think I'm okay. I think I'm all right. So it might be worth just checking where that was. And then, of course, we do the whole thing with e's and lunds. So doing all of that work with indices and logarithms before we introduce e's and lunds, and then later, probably in year 13, when we come to e's and lunds, doing exactly the same thing. And so I'll leave this slide for you. I'll leave this as a slide for you to experiment with. And they all have nice simplifications. Of course, and obviously you can check them on a calculator. Students can check them on their calculator if they wish to, but they're much better if they didn't, for the obvious reasons. But again, they're not going to do questions like this successfully unless they've done lots of practice with questions like that and questions like that earlier on. Why would you have to do a question like this? Well, I mean, it's not directly relevant, but if you think about things like work out turning points, if I give you a curve like y equals x squared ln x and ask you for its turning points, well, we're going to end up getting an answer for x in terms of e, say, and then substitute it back into to find the y coordinate. So, if we differentiate, it's going to get 2x ln x plus x squared over x is 0. Now, when I solve that, I'm going to get an answer for ln x equals, i.e. x will be in terms of e, and then I'll substitute that back into there in terms of e. So you can see perhaps that's where these sorts of expressions will arise. And again, like with the earlier question about the quotient rule, if they haven't done the practice, they haven't got that muscle memory of what to do, they're not going to be able to pull it out of the bag in the middle of the exam. Okay, so I'll leave you to play around with that. I can share the answers with you that next week beforehand. So I just want to give you a bit of rationale, a bit of theory for what I'm talking about. So as you may remember, depending on your training, the work of Richard Skemp, and he says this. He says that if learning is going to happen, then when we encounter something new, we either kind of expand what we already know, and that's called assimilation, or we kind of reboot what we know. We start again. We, like earlier, we turn off our iPad and start again, and that's called accommodating that new knowledge. We sort of enlarge our maths worldview to accommodate the new knowledge, the new learning. I think here's a really simple example. So children in primary find the area of rectangles by multiplication, and then they start to find the missing dimension by division. So what times 5 equals 20? 4 times 5 equals 20, because to find it, I do 20 divided by 5. So finding the missing length is about division. And then we do the same thing for triangles. Now, it's a little bit harder, so you have to remember to double first. So a triangle is half a rectangle. So if the area of the triangle is 10, the area of the rectangle will be 20. So the base is 5, so the height will be 4. But it's so apart from that little wrinkle at the beginning with the doubling of the area value, it's still the same process. We still find the height by dividing. So how do we find the height of a square? Well, whatever we do, we don't divide. Okay, you do get a lot of 25 divided by 4, 6 1/4, because they want to do a division. So the only division they can think of is 25 divided by 4. So yes, they are mixing up area and perimeter, but that's not really the issue. They are taking the method which has worked hitherto, the assimilated method, which is you find the height by division, and they're applying it to a context where it doesn't work. So they're sticking with assimilation. They're not accommodating this new example, this new category of problem, squares, where you have to have a different approach, obviously square rooting. And that's Skemp's example. And assuming I've explained it well, I think it's really powerful. Can we think of an A-level example? Yeah. So 3 times 4. So young children, primary children will often think of 3 by 4 as a grid. They might even think of it, first of all, as an array of counters. They might even think of it, first of all, as literally 3 rows, each of 4 counters. And then those kind of counters like sort of melt in the sun. They splurge out to make an array, a 3 by 4 array, and hence an area. And then when we come to 3a plus b in secondary, in key stage 3, we can think of that as an area. So that's got area 3a, and that's got area 3b. So 3a plus 3b is the same as 3 brackets a plus b, all the way around. 3 plus a plus b is the same as 3a plus 3b. So we've assimilated our new calculation, our new representation has been assimilated into our old idea of thinking about multiplication as area. So here we go along in GCSE and A-level, and we hit sine of a plus b and ln of a plus b. And we say, no, you can't expand the brackets because it's not a multiplication. And though that's true, it's not recognizing, I would suggest, what's happening, which is what they're trying to do is they're trying to assimilate this into this picture somehow. And of course, there is a picture. I mean, you can draw a picture for sine of a plus b. It just looks like that. It's got nothing to do with area, or not very much to do with area. Obviously, those triangles have got area. They've not got very much to do with area. So we can assimilate. So they're trying to assimilate, but it doesn't work. And what they're not doing consciously, deliberately, forcefully is accommodating and kind of pushing back their boundaries of knowledge, forcing out their understanding frontiers to recognize what we mean when we say this is not a multiplication. This is a function operating on the brackets. There's a function of a plus b rather than the operation multiplied by 3 acting on a plus b. So I think I would suggest, obviously Skemp would probably may well disagree with me, but I would suggest this is an example of what he's talking about, whereby we can go to expanding brackets by assimilating expanding brackets into our prior understanding of multiplication. But then we don't accommodate when we come to something. So when we come to sine or ln of a plus b, that not only we sort of say it's not a multiplication, but that tells me what it's not. It doesn't tell me what it is. So I don't accommodate the whole new idea of a function with 2 arguments, of a function with 2 operations. And I think that's where things start to unravel. This, depending on where you were trained and when you were trained, may well remind you of Vygotsky. So Vygotsky had this idea of the zone of proximal development. And so if we want people to learn, they've got to learn things that are just beyond where they are at the moment. So it's just that one next step, that one small change that takes them just beyond where they are at the moment. And that's not happening there. The jump from 3 brackets a plus b to sine brackets a plus b is an enormous jump. That's not going to happen automatically. That's not going to happen naturally. There has to be explicit accommodating work taking place to fit both of those apparently similar but actually very different looking expressions very similar looking but mathematically very different expressions into the same maths head, into the same maths brain. what I was going to do now was just look at some questions from the practice sheet. I'm going to talk about algebratization. So all three of these questions really lend themselves to reinterpreting as algebraic expressions. And I would really like to do that, but because of the slight glitch in the middle, I haven't really got time to do that. So I think I might park these, and I will come back to that. So the end of next time, I will stay behind at the end of next time, and I'm very happy for anyone who's got any questions about the practice questions to come and ask me about how I go about doing them. Perhaps a hint, if you want a hint, is forget about 101, think about x. So what you've got here is you've got x squared subtract 1 over x plus 1. And here you've got x squared subtract 1 over 25. Well, maybe the 25 will come out in the wash. And then here you've got x to the 4 subtract x squared over x cubed subtract x squared. So kind of take it from there. So that's what I mean by algebratization, which is look at the structure of this algebraically rather than specific values. And then 9 and 10 we can come back to next time if you would like to. So in conclusion, I hope I've demonstrated examples of what I mean by, say, desirable difficulty, what it should look like, of distinguishing between tactics and strategies. I hope I've explained, I feel I haven't done a full service, I hope I've explained a bit what I mean by accommodate, don't assimilate. Force open, explicitly challenge their assumptions that they can translate GCSE and earlier knowledge into the A-level context. In terms of getting the maths from them, what questions have I asked a lot during the day? Sort of what questions have I asked sort of rhetorically? Those are my favourite questions, and particularly those two, slightly in bold, now in purple. What's the same? What's different? What do you notice? Those are the questions I'm asking all the time to draw out their response. You know, what are they seeing in the mathematics? What are they noticing in the mathematics? How is that telling them what to do? I'm really happy to take your question, but as I said, I am Mr. Rush. I do have to go really quickly. If you want to put your questions in the chat, I can definitely ask them by email. I will put my email in the chat now. So if you want to email me later at kcl.ac.uk, I'm really happy to take questions from people later by email. And next week on Wednesday, I will hang around till midnight, possibly midnight, as much as you like to answer your questions. So please do email me in the chat if you want to. Sorry, email me if you want to. Put it in the chat if you want to. Or I definitely might begin next time with a bit of Q&A as well. I do need to say thank you. I do need to rush off in about 2 minutes' time. So I hope that's been of some use. There's a valuation link. Oh, crikey, I forgot the valuation link. Right, don't go anywhere yet. I've got to give you the valuation link, otherwise Emma will be really cross with me. Right, so I'm going to, it's to hand on my email. I just need to get it. So if you just wait a moment, please, folks. So it would be really useful to get your evaluation, not least because in the evaluation, there's a really key question, which is, you know, what was it okay? What can I do better next time? So I'd really grateful because someone please click on the link and check it works. Check the link works. Can someone just tell me that works? I've copied it correctly. I missed a slash up at the end. Maybe I need the slash at the end. Is it working for at least one person? So Emma and I would hugely value your comments. The scores and the doors, of course. Oh, thank you. Thanks, folks. Okay. So if you could take 5 minutes now, particularly the box at the bottom, what was good, what was effective. So the two boxes at the bottom. What are you going to take away? And if you want to give me any feedback before Wednesday, now is your chance to do it because I'm now going to disappear, which is terrible. So bye. I hope at least some of you come back on Wednesday. We're going to think about graphs, and it'll be a little less breakneck speed because I won't be so worried about the stopping point. So purple triangle, off I rush. Thank you for your time. I'm going to have to close the meeting because I'm the host. I need to go into another meeting. So can you all please click on the link, and also click around if you've forgotten it. Please click on the link. Please fill in the feedback. You'll get the slides. Really looking forward to seeing you next week. Bye for now.